Students, I welcome you in today's class of physics. As you know very well, in yesterday lecture, we had covered out this chapter, most of the topics of the chapter number 15, which is your refraction of light at a plane interface and the total internal reflection which is going takes on optical fiber. Fine. So, in yesterday class, we had covered out the refraction of light at a plane interface. Clear? We had discussed already the what happened when the lights go from one medium to the another medium. It's bent towards the normal. Here you can see in the figure number 1, and it also bends away from the normal. Clear? These are the some points we had already discussed in our previous lecture. I already told you the Snell's law. What's the Snell's law is? Fine. So, now today's lecture we will discuss the forward topics of the chapter, which is your refraction of light through a rectangular glass slab. Clear? So, here this is the thing we have to discuss today. So, as you can see here, this is the figure. Let ABCD, you can see here, represent a parallel side glass slab. Fine. We considered here a ray of light passing through air through the glass slab undergoing refraction. Here you can see an incident light which is P. Clear? This is the incident light coming from the medium. So, we are considering here a ray of light passing through from air through the glass slab undergoing refraction and then entering again in air. Here you can see when a light incident from air on a glass slab, and after refraction it here you can see at point R it goes again into the air. The ray undergoes refraction twice, one at the surface AB and then at the surface DC. Here you can see this is the surface AB and this is your surface DC. Clear? So, here in figure 3 shows the path of light ray through the glass slab. The incident ray is your PQ. Here you can see this is the incident ray PQ, and QR, this is your QR is your refracted ray. So, and RS is the emergent ray in air. Fine. As you know very well, Snell's law. What is Snell's law? Tells about using Snell's law at the point sin I by sin R1 equals to A and G, means the refractive index of glass with respect to air. Clear? This is your equation number 1. For refraction at point R of phase DC, we consider here sin R2, because here the angle of refraction is how much? R2. Here you can see is equals to refractive index of air with respect to the glass, that is G and A or A and G. It is reciprocal of A and G, as I told you in the previous lecture. But R1 equals to R2, the medium is isotropic from Q to R. Fine, because here the medium is glass. Clear? That is why we consider here R1 equals to how much? R2, means the angle of first refraction equals to angle of second refraction. We again use here Snell's law. You can see here sin E upon sin R1 equals to A and G. Clear? This is your equation number 2. Now, from equation 1 which we derive above, this one, and from the equation number 2, this one, we get how much? I is equals to E. Clear? That is, the angle of incidence is equal to the angle of emergence. What is E here? E is the angle of emergence. Here you can see. Fine. So, angle of incidence is equal to the angle of emergence. As I equals to E, the emergent ray RS is parallel to the ray PQ. Here you can see the in figure number 4, the ray PQ is this and the emergent ray is RS. You can see in the figure number 4 here. This is the emergent ray, this one. It can be seen from the figure 4 that the emergent ray is shifted or displaced with respect to the incident ray. There is a slight displacement you can see in the ray RS. The perpendicular distance Rm between the emergent ray and the direction of incident ray is called the lateral shift. You can see here a perpendicular Rm. This is the perpendicular, or you can say this. So, this one is the perpendicular. So, this shows the lateral shift. Fine. let the thickness of the slab be T. We are considering here the thickness of the slab is how much? T, that is AD is equals to, you can see here AD is equals to QN. Where is QN? This is QN and this is your AD. We assume it as equals to T. So from right angle triangle QRM, you can see here this is the right angle triangle formation here QRM. Clear? Sin theta is equals to how much? Perpendicular upon hypotenuse. So what is the perpendicular here in this triangle? RM is the perpendicular and QR is your hypotenuse. So we put the value, or you can say we find out what is RM. So RM equals to QR sin theta. Fine. But what is theta here? As you can see, this is the theta. So what is the theta? Theta is equals to I minus R1. Fine. Because I and R1 both are vertically opposite angles. Here you can see this is the vertical opposite angle. So if we have to find out the angle theta, so what we will do here? We write like this, theta is equals to I minus R1. Fine. So in place of sin theta in this equation here, we put what? Rm is equals to QR sin I minus R1. We put the value of theta in this equation. Now we again assumes a right angle triangle which is your QNR. You can see here in the figure number 4, this is also a right angle triangle QNR. Now here we are considering the cos R1. R1 is the first refraction angle and cos theta you know very well is based upon hypotenuse. Clear? So base is your Qn and QR is your common hypotenuse, which is also we considering here in the sin theta. Clear? So in place of Qn we write how much is equals to T, this one, and QR is QR. Now we find out the value of QR here. So how we can write QR is equals to T upon cos R1, and you know very well 1 upon cos theta is equals to how much? Sec theta. So that's why it is written here T sec R1. Clear? Now from equation 4th and 3rd, you can see here this is your equation number 3rd and this is your equation number 4. Fine. Lateral shift, we find out the lateral shift how much? Rm is equals to T sin I minus R1 into sec R1. Clear? Because you can see here in equation number 3rd there is a relation between Rm and QR, and we already find out the value of QR from here equation number 4. So we put the value from equation 4 of QR in equation number 3. So finally we got the relation Rm is equals to T sin 1 minus R1 into sec R1. I hope it is clear. Now we will move to our next topic. This is the refraction through parallel multiple media. Fine. You can see here this is the diagram, figure number 5, refraction through parallel multiple media. Suppose you can see here a light ray OA. Fine. As you can see in the figure number 5 here, this is the figure 5, traveling in a medium first. Clear? First refracted along AB in a medium 2 and then along BC in parallel medium 3. Here you can see there are the 3 mediums. That is why we are considering here the multiple media. The first medium is your air, the second medium is your water, and the third medium is your glass. Fine. So these are the 3 mediums. So that is the thing is written here. So AB in medium 2 and then along BC in parallel medium 3 and finally emerges along CD in its initial medium 1. Fine. Now we suppose here I1 and R1 be the angle of incidence and refraction respectively. Clear? This is your angle I1, first the incident angle, and this is the first refraction angle. At point where? At point A, the interface of the media 1 and 2, which is the interface. Interface I hope you know very well. Interface is a layer which separates the 2 mediums. So we use here Snell's law. So 1 and 2 is equals to sin I upon sin R1. This is your equation number first. Now we consider here at point B. You can see here this is the point number B. and here how much the interface of the media 2 and 3, the angle of incidence. Now the what is the for water, this R1 is considering we consider here as a refracted angle. Now for the glass, this angle is changes into the incidence angle. That's why we are considering here incidence angle R1. Let the angle of refraction be, and for glass the refraction angle is how much, is R2. Then again we use here the Snell's law, so we can write it 2 and 3 is equals to sin R1 upon sin R2. This is your equation number 2 and this is your equation number 1. Again you can see here at point C, this is your point C. Now the same thing happening here. Now R2 is an incidence angle for the point C and I1 is the refracted angle. Clear? So at the interface of media 3 and 1, the angle of incidence is R2. As the various interfaces are parallel, the emergent ray CD is parallel to the incident ray OA. Here you can see the CD is parallel to the OA. And hence the angle of emergence at C is equal to the angle of incidence I1 at A. Clear? Thus we can write here using the Snell's law how much, 3 and 1 is equals to sin R2 upon sin R1. This is your equation 3, this is your equation 2 and this one is your equation number 3. So if we multiply all the three equation, you can see here what we will get, I and 2 into 2 and 3 into 3 and 1 is equals to sin I by R1 into sin R1 by R2 into sin R2 by sin. So if we cancel out all these terms, what we will get here, we will get here equals to 1. Fine. Or you can also write it like this, 1 and 2 into 2 and 3 is equals to 1 upon 3 and 1. Clear? But 1 upon 3 and 1 is equals to 1 and 3, because you know very well, as we talk about in the lecture number 1, there is a reciprocal relation. So we write like this, 1 and 3 is equals to 1 and 2 into 2 and 3. Or you can also find out the value of 2 and 3 equals to how much, 1 and 3 upon 1 and 2. Thus if the media 1, 2 and 3 are air, water and glass respectively, then the refractive index of glass relative to water is equals to how much, this is the refractive index of glass relative to the water. Clear? I hope it is clear for you. Fine. Now we will take here real and apparent depths. You can see here, this is the real and apparent depth, or you can also say that it is a normal displacement. Fine. So an object placed in a denser medium, you can see here, this is the figure. When an object placed in a denser medium and when seen from the rarer medium appears to be at a depth is smaller than its actual depth in the denser medium. Fine. Means if an object is placed in a denser medium and you are seeing from a rarer medium, suppose the rarer medium is air and the denser medium is your water, then what will happen, the object appears to be at a depth is smaller than its actual depth in the denser medium. This is the real and apparent depth. Now why this is happening, this happened due to the refraction of light. Clear? You can see here in the figure number 6, this one, XY be an interface separating a rarer medium which is your air from a denser medium which is your water. Fine. And O, a point object placed in the denser medium. You can see here a point O is placed at the denser medium or at a depth here. Let it be seen from the rarer medium, a ray of light OA incident on the interface normally goes undeviated along AB. Clear? You can see a person is seeing from his eyes, so you can see the ray AB. Clear? Normally goes undeviated along AB. And another ray OC, you can see there is another ray OC. This is the ray OC area going on. On refraction into air, bends away from the normal along CD. So the two refracted rays, one is your AB and one is your CD, appears to come from the point I, which this is your point I, which is the virtual image of object O. Fine. Thus the object which is actually at a depth AO appears to be at the depth of AI. Now this is the apparent depth AI. Clear? And what is the actual depth is AO. Accordingly, AO is the real depth and AI is the apparent depth of the object. This explains why a swimming pool appears shallow than it really is. Fine. Now we suppose here, let I be the angle of incidence in water and R be the refraction angle in air at point where? C point. This is your point number C. The refractive index of air related to the water is given by which law? Is Snell's law. So you can write like this, WNA is equals to sin I by sin R. Fine. The refractive index of water relative to the air is, here you can see that A and W is equals to 1 upon Wn, or you can write like this. Now since BO and NN are parallel, you can see from the figure BO and NN, this is the ray BO and this is the normal NN, clear, are parallel. So angle NCD, you can see from the figure number 6, angle NCD is equals to angle AIC. These are the corresponding angle, and angle OCN dash is equals to angle AOC. These are the alternate angles there. Fine. So we write like this, A and W is equals to sine of angle AIC upon sine of angle AOC is equals to AC upon CI and AC upon CO. Clear? So AC are cancelled out here, so we will get here CO upon CI. Since in practice the aperture of the eye is very small, the refracted ray AB and CD, you can see here AB, this is the refracted ray, AB and CD enter the eye only if point C is very close to the point A. As you can see here, this point is very close, nearer, C point comes closer to the A, then we can see the refracted ray properly, because the aperture of the eye is very small. In that case, CO is approximately equals to AO and CI is approximately equals to the AI. So we can write here like this, A and W is equals to AO upon AI, or you can write it real depth upon apparent depth. Fine. The distance OI is the normal displacement of the object. It depends upon the thickness and the refractive index of the denser medium as below. So we can write form the relation here. Let T be the thickness of the water medium. So AO equals to how much? T. The normal displacement we can show with this relation. D is equals to AO minus AI equals to AO 1 minus AI by O. So D is the displacement. If we find solve the relation, we will get here like this. This is the relation. If there are more than one media between the objects and the viewer, then the apparent depth, if there are multiple media, in that case what will happen? Here you can see they are taking here the multiple media, N1, N2, N3 are the refractive index of the different medium. So the apparent depth is equals to, this is the formula in that case, and the refractive index is, this is the refractive index for that medium. I hope it is clear. So that's all for the today's class, students. We will cover the next topic, which is our critical angle and total internal reflection, in our next lecture. Thank you, class.